Now, Newton's third law of motion, we are completing the chapter 17, Newton's laws of motion and gravitational universal law. So according to Newton's third law, forces always come in pairs. That is, there are no isolated forces in the universe. The forces in a pair are equal in magnitude and opposite in direction. And the forces in pair act on different objects. This is very important. Remember it. We will see it later on. The third law is commonly stated in an abbreviated form. For every action, there's an equal and opposite reaction. Look at this book. So, I have two forces in this figure. The table is applying a certain force on the book, and the book is attracted by the gravity to Earth. So these two forces are equal but opposite in direction. Same magnitude, different direction. So the force of attraction between the book and the Earth is downward. The reaction force of the table on the book is upward. They are equal. Examples of Newton's third law of motion. Flying through the air, birds depend on Newton's third law of motion. As the birds push down on the air with their wings, in turn the air reacts by pushing the birds upwards. So this is a perfect example of Newton's third law of motion. Another example, the baseball forces the bat to the left. This is the first one. This is the action force because it started. And the bat forces the ball to the right. This is the reaction. So as you can see, they are equal in magnitude but in opposite direction. Okay, the size of the force on the air equals the size of the force on the bird. The direction of the force on the air, downwards, is opposite to the direction of the force on the bird, upward, and action-reaction force pairs make it possible for birds to fly. This is concerning the previous example. Now, if action and reaction force pairs are equal and opposite, how can anything move? Won't the action and reaction forces cancel? This is a very important question. This is why I told you pay attention for the previous sentence, because each force is acting on a certain object. Action and reaction, they are forces that don't cancel. Why? The answer is no, they don't cancel because each one of them is acting on a different object. Forces can cancel only if they act on the same object. So if you remember the example of the book and the table, let's go back to it. So the book is applying a force and the table is applying a force on the book. The first force, it's the attraction between the book and Earth. So I have these two objects. In the second force, I have the table applying a force on the book. So the two forces aren't applied on the same object. This is why they don't cancel. Okay. Now, a bug with a mass of 5 grams flies into the windshield of a moving 1,000 kilogram bus. Which will have the most force? The bug on the bus or the bus on the bug? At the first moment, you might directly say, of course, the bus on the bug. In fact, the answer is the force would be the same because the force of the bug is the small mass times the huge acceleration, whereas the force of the bus equals the huge mass of the bus times the small acceleration compared to the acceleration of the bug. So both of them are going to be equal in magnitude but in opposite direction. Now, let's review the laws of motion. The first law, objects in motion tend to stay in motion and objects at rest tend to stay at rest unless acted upon by an unbalanced force. Newton's first law, net force equals to 0. Newton's second law, force equals mass times acceleration, F equals ma. Newton's third law, for every action there's an equal and opposite reaction. Now, the last law, it's Newton's law of universal gravitation. So Newton was sitting under an apple tree when an apple fell down from the tree on the earth. This sparked the idea that the earth attracts all bodies towards its center. He declared that the laws of nature are the same for earthly and celestial bodies. Newton wrote that the sight of a falling apple made him think about the problem of the motion of the planets. He recognized that the apple fell straight down because Earth attracted it. Newton was so confident that the laws governing motion on Earth would work anywhere in the universe that he assumed that the same force of attraction would act between any two masses ma and mb. So any two objects attract each other with a gravitational force proportional to the product of their masses and inversely proportional to the square of the distance between them. The force acts in the direction of the line connecting the centers of the masses, which is the center of gravity of the object. I have two objects, two balls. The first one has a mass m1, the second one has a mass m2. The distance between them is r. According to this law, these two objects are going to attract each other with a force F. F1 equals F2 equal to G times M1, M2, the masses, the product of the masses, over R square, which is the square of the distance separating their centers of gravity. Now the value of G, it's a constant. G equals 6.67 times 10 minus 11 Newton meter square per kilogram square. F equals G capital M, which is MA or M of the first object, small m over R square. F equals the force of attraction between the two particles. M equals the mass of the first particle. This is capital M, and small m is the mass of the second particle. R is the distance between the centers of the first and the second particle, and G equals the universal gravitational constant, which is 6.67 times 10 minus 11 Newton meter square per kilogram. Now, the distance between a 40 kilogram person and a 30 kilogram person is 2 meters. What is the magnitude of the gravitational force each exerts on the other? Universal constant is 6.67 times 10 to the power minus 11 Newton meter square per kilogram square. So in order to find the answer of this, the force is equal G times M1 times M2 over R square. You just have to replace. G is given, M1 is 40 kilogram, M2 is 30 kilogram, and R is 2. You have to square it, so it's 6.67 times 10 minus 11 Newton meter, without the units, times 40 times 30 over 2 square, and you will get the answer. So F equals G M1 M2 over R square, 6.67 times 10 minus 11. This is the G. M1 is 40, M2 is 30 over 2 square, and the rest is calculation. Determine the force of gravitational attraction between the Earth, this is the mass of the Earth, and 70 kilogram students if the student is standing at sea level, a distance of 6.38 times 10 to the power 6 meters from Earth's center. I'm sorry about the exponents, So the mass of the Earth is 5.98 times 10 to the power 24 kilograms, and the distance is 6.38 times 10 to the power 6 meters from Earth's center. So I need the force. F equals, first you put G, second you put the mass of the first object, which is in this case the mass of the Earth, and the mass of the second object, which is in this case the mass of the student, over the distance to the power 2, and you'll get the force 686. The rest is calculation. And that's it. Thank you very much. Grade 10.